Thank you. So this is a very unusual sort of conference for me to attend. Normally I'm at theory conferences, but here is a place where people are really doing stuff and making things happen. Now it might seem that the last talk, the last speaker and I have very little in common apart from our hairstyles. But in fact, both of us are concerned with making sure that things work the way they're supposed to. And this is what verification is all about. Verification is a branch of what's called formal methods in software engineering, and it's been the subject of quite a lot of debate. So what I'm going to talk about today is what are the prospects for actually doing it in practice and in an automatic way. So one of the wise old men of computer science is Edgar Dijkstra, now deceased, and he said many interesting things. Some of them quite rude, but two of the ones that can actually be repeated in public are, it is easy to write efficient programs if it doesn't have to be correct. Okay, so people who've written any kind of distributed program know this. If you don't have to worry about things being correct, then there's no problem implementing it efficiently. Somebody mentioned the Paxos algorithm in the question period at the end of the last talk. This is one of those fiendishly clever, incredibly hard to prove algorithms invented by Leslie Lamport. And indeed, in my verification class, the last time I taught it, term projects was trying to explain why this algorithm works correctly. So, if you really want your program to be correct and efficient, you have quite a lot of work to do. Another one of Dijkstra's wise sayings is that testing can show the presence of bugs, but it can never show the absence of bugs. It just shows that you failed to find them. They might still be lurking there. Okay, so you need something else to really be assured that things work the way they're supposed to. So let's focus on this word correct. What does it mean exactly? So first of all, it needs precise language. People speak far too sloppily. This is one of the standard rants I have in all my classes. People just speak too imprecisely. So in order to really have a formal notion of things being correct, you need a precise specification language. And this is usually some form of logic. So I will mention a bit about temporal logic later on. One also needs a precise formal execution model for what programs do. This is called formal semantics. And it's one of the areas of research that I work in. Having got these two things, a precise specification and a precise semantics for program execution, then you have to have a proof that the program meets the specification. Now, proof, of course, is an intimidating word for many people. I personally find it very attractive, but indeed for many people, it's a turn-off. And I would like, therefore, to explore the prospects of doing these things automatically. So the first thing people tell you is, that's impossible. First of all, programmers are not trained in formal logical systems. That's easily fixed. Just make them take my class. I welcome all 6 billion of you. One often hears this being said, no one in the real world uses it. I did not realize that I lived in a virtual world. But apparently many people claim this, with perhaps some degree of truth, but not in the categorical way that they state it. They also tell you that it's impossible in practice, but as Alice said, you should try to do 6 impossible things before breakfast. So there's no reason not to do something because it's impossible. Now a lot of people just say, why bother? You just reinstall the app and then it'll all work fine. So this actually happened. I was looking up the bus schedules to get here, and of course the app said, oh, I need to download a new schedule, and then it stalled. And so the only thing I could do was reinstall the app. And indeed, then I finally got the new schedules and caught the bus and made it here on time. Okay, so how about automated proof? Unfortunately, those fiendishly clever theoreticians did the following. They proved that you cannot prove the correctness of programs automatically. This, of course, begins with Alan Turing's seminal work in the 30s about the impossibility of solving the halting problem. I used to have a hoodie that said on the back, I do not know whether I halt or not. And people used to stop me on the road and say, what does that mean? And I would start explaining, let's see, here's what a Turing machine is. And then they would slowly drift away. But fundamentally, this is a fact. There's a powerful theorem called Rice's theorem that says any interesting property of programs cannot be done automatically. Any, not just the halting problem, any problem. The only two problems that can be done are the two trivial problems where you say everything has this property and nothing has this property. So these can both be done in constant time. But apart from that, nothing can be done. So the halting problem is algorithmically unsolvable. Arithmetic is incomplete. Even humans can't possibly write down a formal system in which everything in arithmetic can be proved. So what hope is there? Right? So as I said before, just because something is impossible doesn't mean you shouldn't do it. Okay, so I was a consultant for the avionics industry some time ago, and these are the people who write flight control software. So I was actually, at the time, surprised to find out how much of this is automated. So apparently, the pilot does very little in most flights, including landing. Now, if your plane is dependent on flight control software and there's some glitch in it as it's about to land, you can't reinstall the app. It's a bit late for that. So I remember asking these people, so the reason they brought me in as a consultant is because they were writing so-called safety critical software, and they were not happy with just testing. There were all kinds of certification issues happening with the Civil Aviation Authority, and they wanted to know what were the prospects for formally verifying the correctness of safety critical software. Okay, so I asked them, so what's your current methodology? So they said, yes, we have meetings. So this did not, I was tempted to cancel all my flight tickets after that. But I said, what about if it's really critical? Then they said, yes, then we have lots of meetings. So clearly something needs to be done when lives, or even more importantly, money is at stake. So let me mention some famous disasters in the software world. So all of you have probably heard about this. This is the beautiful Ariane 5 rocket created by the European Space Agency. It cost, 3 billion euros or thereabouts. And it was there on the launch pad, ready to go. This is what it looked like just before takeoff. And this is what happened shortly after liftoff because of a floating point bug. Okay, so fortunately it was unmanned, so at least no lives were lost. So here is another story that perhaps not so widely known. So there was a near disaster in the NORAD system. So I don't know if all of you have heard of NORAD. It's the North American radar defense system that used to exist in the days of the Cold War. I hope this is large enough to be readable. So it's a really clever scheme that was set up in the 60s. When the threat of nuclear attack from the Soviet Union loomed large in the minds of people in North America and the US and Canada. So this system was set up. You have a chain of radar stations all across the north of the continent, tracking incoming possible missiles from Russia over the pole. So if these things are detected, then immediately a bunch of anti-ballistic missile sites are activated. So there are many of these anti-ballistic missile sites activated, and the idea was that these anti-ballistic missiles would be fired in response to the incoming rockets. They would blow them up in midair, and the nuclear debris would fall harmlessly on Canada. So this thing that happened in 1980 is absolutely true. January 3rd, 1980, without warning, all the alarm bells suddenly started ringing at the centers. The bay doors opened, the anti-ballistic missiles came up, ready to fire, and if Jimmy Carter had been on the ball, he would have pressed the button. But they were armed and ready to launch, so they were worried, what the heck is going on? They checked, they found there were nothing actually coming, so they realized it was some kind of bug, software bug. So they shut down the system quietly and rebooted everything. So they said, okay, that was a bullet we dodged. 3 days later, it happened again. Fortunately, we're still here. But this is an example of something truly catastrophic. I still don't know if they have actually traced what happened. It's never happened again, fortunately. And lots of these things are classified anyway. But there's a nice book called Safer Sea, written in the 80s, which describes this incident. Okay, so that's so much for just reinstall the app. This particular app, they did reinstall, and it came with the same bug. So what can we do? So correctness of general programs is indeed impossible, but many programs are not fully general. Do we really use unbounded memory all the time? Quite a lot of things are simply finite memory programs, especially in hardware, right? So many things are so-called finite state machines, and for such things, actually all those so-called undecidable problems become decidable. Many algorithmic things can now be done, right? Might still be intractable, but everything is possible. Let me tell you another story, this one about a finite state machine. This is the infamous Pentium bug. So Intel released in 1994 a new Pentium chip, and it was the latest and greatest thing. But there was a subtle bug in the design which caused floating point multiplication to sometimes give the wrong answer. Not always, but sometimes. So you'd actually have to massage it quite a bit to find this out. If you were just balancing your checking account, it would be okay. But if you're trying to do high performance numerical simulations, it would show up, and somebody found it. So then, so I shouldn't make it sound like it was such a stupid thing, because this algorithm is actually complex. It's 40 pages to write down the floating point multiplication algorithm as they implemented it in hardware, and some of it involves a table lookup. And what happened was they accidentally left off a small piece of the table. Okay, so that was copied incorrectly. It cost Intel about $400 million. That was 1994. In today's money, that would be a lot more. And it led to a huge loss in their reputation. It led to jokes like, Intel redefining the future of computing and of mathematics. So these are the kinds of things that one can't afford. So the technique that one can use to actually determine the correctness of this kind of software is called model checking. It was invented by Ed Clark, Alan Emerson, and Joseph Sifakis back in, this should be 1981, not 1918. I told you there were bugs everywhere. So it was invented simultaneously by Ed Clark and Alan Emerson, and independently by Joseph Sifakis, also with other collaborators like Suzanne Graf. So the three of them were given the Turing Award for their contributions to model checking. Now, when it came out, that was 1981, as I said, not 1918, it was a theoretical curiosity. They gave this algorithm that could exhaustively prove the correctness of finite state software with respect to specifications in a particular formal language called temporal logic. I will show you a tiny bit of temporal logic presently. And it remained a theoretical curiosity. They actually did an implementation, and they were able to check a 12-state system or something, or a 2-bit adder, something like that. They were able to do toy things, and nobody took it that seriously until the following thing happened. So Ken McMillan was a graduate student at Carnegie Mellon University Computer Science Department. And they have a very interesting way of starting out the PhD program at Carnegie Mellon. They don't have courses right at the beginning. They have this thing called the immigration program. So what happens is that for about 6 weeks, you don't take regular classes coming in. You get a couple of lectures from every prof in the department on all kinds of things. So you're blasted with all these different things, most of which you don't understand, because they're all talking about their latest research. By chance, Ed Clark was talking about model checking, and Ken McMillan was listening. Shortly thereafter, an electrical engineer also working with the computer scientists presented a technique for modeling hardware using a particular data structure called binary decision diagrams. Okay, so Randy Bryant invented these binary decision diagrams, and Ken McMillan, just because he heard these things in quick succession and because he's really smart, he realized, aha, this thing that's designed for hardware modeling, I can use it for model checking and actually do realistic, large-scale systems efficiently. Okay, so this created a kind of revolution, the binary decision diagram revolution, which is truly remarkable. So what were the things they were able to do? They were able to do large systems. So if you remember, I said before, a few states, few tens of states. Maybe if you really put your mind to it, you could get a few hundred states. Ken Macmillan pushed it up to 10 to the 200 states. So this is taking it out of the toy, the theoretician's playpen, and into the so-called real world. In fact, if you use abstraction and partial order techniques and other such clever things, on-the-fly calculations and so on, they have even successfully verified 10 to the 600 state systems. By the way, 10 to the 600 is not as impressive as it might sound. 1800 bits will get you there. So still, it allowed them to check, for example, the bug in the Pentium chip. Now, of course, they found it after the disaster happened, and they wanted to do a demonstration of what they could have done had they had been asked to check the correctness of this algorithm. So they took the model of the Pentium chip, and they ran the system. I think it took about 24 hours of CPU time before they uncovered the bug. It's not so simple as I'm making it sound. I'm making it sound like you take the system and you press a button and it'll tell you yes, no, like an oracle. You have to spend a significant amount of time building a reasonable model of the system, but nevertheless, that huge intractable proof, certainly beyond the scale of human effort, can indeed be done automatically. Certainly this was a hit with Intel, as you might imagine. And one of the reasons why we don't hear quite so much about hardware model checking these days is because Intel hired practically everyone working in it, shoved them into their lab, and we don't really get to talk to them as much as we used to. But we know that a lot of research like this is happening there, and at other places, all the major hardware vendors have heavily invested in model checking technology. So at least in the hardware world, this is happening. Now, one thing about hardware is that it's very regular. One doesn't write a huge, massy spaghetti circuit, right? They tend to be very regular repeating things with some regular structure which is exploited. That's how you get to things like 10 to the 600 states. So what is this model checking thing? So briefly, you write the system description as a finite state machine, which, as I said, is adequate for many, many, many things. Most protocols, most communication protocols, most synchronization things, most concurrent programs, these are finite state protocols in action. So finite state machines suffice to describe them. And in fact, you don't draw them as little circles and arrows like I teach in class. You actually are able to compile into finite state machines from whatever higher level programming language you're using. You write the spec in something called temporal logic. This word temporal says that the notion of time has been built into the logic so that you can actually talk about executions in a convenient way. And the model checking algorithm then takes the specification, takes the system description, and tries to prove the correctness of the program. Technically, instead of trying to prove a theorem, as theorem provers tried to do and basically failed, this is trying to show that the system that you have is a model of the formula. Okay, so that's why it's called model checking. It's checking whether this thing correctly models the formula. In effect, what it's doing is exhaustively checking every possible execution of the program. Stated like that, it sounds uninspiring, but indeed, it's quite a bit more clever. In effect, it does this. What it actually does is involves some beautiful mathematics, actually. Fixed point theory and all other cool things that I will tempt you with but not explain. So what does temporal logic look like? Well, it has the normal notions of logical connectives and, or, implies, negation, and so on. But in addition, it has 4 operators that you can attach to statements. The whole point about temporal logic is that the truth of a formula changes in time. And this is going to happen because you've got a system that's actually executing and making changes. So you can no longer say things like, is x equal 1? Well, x might be equal to 1 now, but after people have done updates, it might not be. Right? So you have to have a notion of time built into your actual specification, and this is the crucial part. So it turns out a lot of experience with writing specification has led to them distilling out these 4 as being the fundamental things one needs to say. So you need to have something that allows you to say, in the next state, this will be true. Okay? So when you write down a formula and you say this formula is true, implicitly you mean this formula is true now. And if you want to say it's true in the next state, you put a circle in front of it. Okay, so you can actually write a formula that says, maybe this is not true now, but it will be true one time step from now. Then the box symbol means this formula is always true. It's what's called an invariant of the execution. All kinds of things might happen, but this particular relationship will always hold. And this is something you often want to do, especially when you're writing concurrent programs. You would like to say things like, it is always possible for my program to do something, otherwise you're deadlocked, right? So you would like to make statements like that. The diamond symbol stands for eventually. At some future time, the actual value unspecified, such and such will become true. And finally, the last one is the most tricky one. It actually takes two arguments, and it says the first thing will stay true until the second thing becomes true. And this is very, very important for capturing the fundamental idea of locking. You want to lock some structure until something becomes safe. You want to lock some property until something becomes safe. Until allows you to do that. It turns out until is powerful enough to actually express all the things above. And but nevertheless, it's convenient to have everything above it. It's surprising how intricate the theory behind this is, but at the superficial level, it's not difficult to understand what these formulas say. And what people have learned from trying this out in the field is that engineers are quite happy writing specs in this language. The one thing they have trouble with is when you put an until inside another until. And this is indeed tricky to follow, but apart from that, most formulas written in this are perspicuous as well as fully formal. So in fact, I remember asking the avionics engineers to write down specs. A lot of them were writing down all kinds of fairly garbled things, especially about timing, and timing is critical. So there are many extensions to temporal logic where you actually put quantitative time. This is a kind of qualitative time. It's talking about eventually and always and until, but you might want to say in 10 seconds from now if you want to do real-time programming. You might want to say also probabilistic things with high probability this will happen within 10 seconds, etc. So all those kinds of extensions also exist. Let me just show you a very simple typical spec. So you might want to say something like, it's always true that if you request something, then sometime in the future it will be granted. Okay, so this is a property you would like to hold in your program. So, of course, one likes to say more interesting things as well, but this is a very basic one, and as you can see, it fits nicely into the temporal logic paradigm. So, in words, every time a request is made, it is granted sometime in the future. And model checking can take a formula like this, run it through, and tell you that your system has this property, a useful thing to know, because quite often when you just hack concurrent programs, this is one of the properties that you fail to check, or you kind of vaguely think you've checked it, but once these things start getting complicated and once you have interacting concurrent threads, then it becomes difficult to check. So I was really fascinated by the previous game talk because it seemed to me that's a scenario where all these kinds of complexities are going to manifest themselves very soon. Okay, my chair is telling me to get a move on. So who uses this stuff? So hardware companies, as I mentioned. What about software? I talked about the regularity of hardware. What about software? It's much more irregular, and that makes it challenging, and hence much more difficult, and hence it's been done much less than hardware. Nevertheless, we have several verified compilers in existence today, and indeed operating system kernels that have also been formally verified. So many things like this are now appearing, and at least 4 companies that I know that are very actively exploring software verification are IBM, Microsoft, Amazon, and Facebook. All actively, usually they've done this by buying a startup or something like that, but Microsoft actually developed in-house software tools. So there's a famous tool from Microsoft called SLAM that's now used in their production code to verify device drivers. So not just the Fibonacci function or something stupid like that. We're actually verifying device drivers. I'm very proud of this because this tool was developed by 2 people, Sriram Rajamani and Tom Ball. Tom Ball became very famous for this work, and I remember seeing Tom Ball at a conference standing there looking like rock stars tend to do, you know, with this aura around him. And then he walked up to me and said, "Hi, Prakash, do you remember me?" And I was going, "What?" "No." He said, I took programming languages from you. So, So you see, anybody here might also one day be making some such amazing contribution. One of the subtleties that happens in software is reasoning about those damn pointers. They point all over the place. So Laurie Hendren, whom you saw yesterday, actually came up in her thesis with a remarkable new technique for analyzing the behavior of pointers. And her techniques, which are based on the calculus of regular expressions. Now, she is, unlike me, not a fan of theory. She did the theory kicking and screaming in complaint, but nevertheless, she too found it useful, and the algorithms she came up with are now included in many C compilers, including GCC. And it's very useful for the static analysis of pointer programs. So there has been some progress, even in these irregular structures. More recently, some people, John Reynolds, Peter Ahern, and David Pym. John Reynolds recently died, 2013, I believe. Peter Ahern is a Canadian. We lost him. He went to the States. No, sorry, he went to the States, but then he left and went to Britain, where he is now. He invented, along with these other two, separation logic, which is useful for reasoning about heap structures in general and pointers. And they were able to verify grungy, low-level assembly code, somewhat in the spirit of SLAM. They formed a startup called Monoidics to verify the correctness of low-level code, and then this company was bought out by Facebook UK, which is where now that system is used in development. So this past summer in Kyoto, Peter Ahern was giving a keynote talk at the Logic and Computer Science Conference, and was describing how he went from the most abstract math, which is what he was trained in, to Facebook engineering. It was called From Category Theory to Facebook Engineering. It was really inspirational for people like me. He has also been a student in one of my classes, and he had his revenge by twice calling upon me and asking me questions that I couldn't answer, and then it became the fashion in the conference to ask me impossible questions. Okay, so a few parting thoughts. I don't know if we will have time for questions. If there, I will leave it up to the chair to decide. But first, much more needs to be done. My main purpose was not to give you a technical talk, but to try to get you excited, especially the people who are hackers, because we need people who think mathematically and implement non-trivial systems. I tend to attract mathematicians to work with me, and they all say, oh, don't actually write code. Now, this is not much use if we are just going to sit around proving sterile theorems. We need to make these mathematical ideas go into things that actually work. There is no silver bullet. By no means am I suggesting that this is going to solve everything. It absolutely won't. We have to combine formal methods with traditional approaches like testing and with other things. And there's much more to be said about other kinds of programs as well that I haven't mentioned: real-time programs, reactive programs, concurrent programs. So all three of those things were relevant for the previous talk. And the last slide, I thought I would say something inflammatory. So there are the flames. So perhaps we should teach formal methods in law school so that lawyers can sue developers for not using them. So that is one way of making sure that they catch on. Okay, thank you.